Hi, it's my pleasure to give this talk, and my title of my talk is Learning Assist Condition Assessment of In-Service Utility Pole. Before my talk, I would like to acknowledge my co-author, Dr. Yang Yu from UWS, Dr. Ulrike Deckmann from UNSW. This is the outline of my presentation, and I'm going to give you some brief introduction and lay down the challenges for this condition assessment of timber pole. And then we quickly go to the machine learning, not technical detail, but what we have been using, and then focus on the result and the field testing and the evaluation result. We have over 6 million utility poles in Australia, form a critical infrastructure for distribution of the power and communication. And over 80% those utility poles are the timber poles. During the lifetime of those utility poles, they will experience various type of the damage, deterioration, and aging, and so on. And as a fact, industry each year will spend $40 to $50 million to maintain this facility and in order to keep the normal operation. As to current practice, there are visual inspection based practice, and it's called SDD, stand for sound, dig, and drill. The major part of this inspection is digging half meter in the hole and around the pole, so for timber pole, so they can drill and through it to test the material deterioration. And there are some major problem with this, and one of the major problem actually is, you can see the problem here, but one of the major problem is actually this kind of method is semi-destructive. As a result of inspection, actually, it's weakening the pole and seriously, and then together with deterioration, and often cause failure of a pole, as you can see from this example. There was no shortage of the new technique and developed, but none of them so far is reliable and efficient. So what are the challenges? Why we are in situation and like this? And I think the main problem first comes from the material itself, as timber. Timber, as you can see, put down here, is multi-component, hygroscopic, and anisotropic, inhomogeneous, discontinuous. So those are the big enemy for engineer, and particularly for structure engineer. So if you look at the different direction, even look at the Young's modulus, and in fiber direction or in the tangential direction, and they are up to 22 times different. Not mentioning we have the natural defects around here, and as you can see. If you look at the wave propagation, which one of the major actually principle for most of the condition assessment method, and the wave propagation inside the timber pole will be affected by different material property along the cross fiber and along the fiber and cross fiber direction, and the environment impact also seriously, because this material itself is hygroscopic, and not mention about the natural defect, and we have annual growth, rain, and the different material from softwood to hardwood and so on. So that's one big headache. Okay, in addition, we also need to understand the complex of the wave propagation due to the practical constraint in the operation field. So ideally, you would like to impact from the top of the poles, and which is 12 meter and in length, but you can't. And not mention about the live, the wire here and electrical live one. So it's definitely impossible. So standard practice is we impact around up to 1.5 meter area. So if you impact a pole and in that direction or induce some excitation, likely you will induce not one but three type of wave, and the longitudinal wave, bending wave, and surface wave. And also need to mention it wave goes to two directions after impact this point, and it's bi-directional wave, one going up and then reflect back, and one going to bottom, reflect back and meeting somewhere and keep going like that. So if you go study a little bit deeper into wave propagation, wave type mode, and then you realize actually you have more than one type of wave mode. So even the longitudinal, which is P wave, and you could have more than one, okay, type. So the problem we have is only very beginning part, P wave is non-dispersive, means the velocity doesn't change and along the different frequency. Other type of wave are dispersive. So what difference between the dispersive wave and non-dispersive wave? Most people probably imagine the wave propagation and as non-dispersive quite intuitively, because you can see wave doesn't change frequency and pattern. But if you have, in most cases, dispersive case, you can see the pattern frequency will change and along its propagation. So that makes things much more complicated. Let's look at an example, a simple example, and simple means, yeah, it is orthotropic. We model this timber pole numerically, and it's a healthy pole, no damage, right? And we're modeling it as orthotropic material. And so when we actually output all the results, and which numerically, so we have infinite sensor and sensing all different part of the pole, and you can plot out the wave propagation pattern, how they do. And it's complicated. Then what we do is we can apply filter to remove some unwanted feature. For example, we use a FIR filter and finite impulse response filter, and then it doesn't help too much. That's all right. And then we can think about a better filter. For example, the FK velocity filter, and then result getting better. And because we can see more dominant wave propagation, we can use as a signature to detecting changing of the timber pole. Remember, we are talking about a healthy timber pole yet. And then we can even apply better one. For example, FI use the predictive and deconvolution type of the filter. But the problem about those filters is, in order to predictive, and then they need to have a kernel which be able to, you need to know some knowledge about the wave propagation, which you don't know, and the true knowledge. So although it looks much better, but it's practically, we publish paper, but practically it's still remaining problem. And those are the time history of those results. And time history means if you cutting a line from here, and then you look at the vertical direction, out of the plane direction, and you get this graph. Okay, now the problem, we have a problem, and then let's look at the field testing. So in order to evaluate what different method and see which one working or which one not working, we set up the field testing, and this is the pole yard. And at this point, I would like to acknowledge our industry partners' contribution and Osgrid, and provide a lot of financial support as well as the in-kind and like the facility and the people and so on. All right, we have 39 poles in the pole yard, and as for testing, and we talk about this
post in detail later on. And we have device we developed, we call the IBAR, and so it is a multi-sensor system. As you see from previous slides, one single sensor would not be able to do you any good. This integrated the multi-sensor and sensing system with acquisition and the display and so on. Won't go to detail, but and the impact hammer, which registers the impact force as well. And then we went to a different method, and we started with a hierarchical and data fusion and frequency response function method and WPAC energy method and ensembled the empirical model decomposition method. Those are not focus of today's presentation. So today we'll probably more focus on the machine learning method, and including the traditional machine learning method like support vector machine and also more advanced like deep neural network. So here is the result and of those testing, and let me explain to you what the result look like. We divide our sample or poles in the pole yard, 39 poles, into 3 sets. Set 1 are new poles, new poles haven't been in service, just directly taken in and then installed on the ground. And then we have second set 2, and is 11 poles, condemned pole from service. So it's already identified as a defect pole, may not be, but it is decommissioned, and then we transport to the pole yard and install there. And then third type pole set is a set actually same as the second set, but we not use this set at all. It's just we leave it out, and then for blind testing. So set 1 and 2, and we can test and take the data and use for training our system. And when we do a test, this result comes from actually is we call it leave one out testing method. So we have 26 poles and combine set 1, set 2, and only use 25 for training randomly, and then we will put one, we testing that one and with 25 training data, and then we swap and 25 times. So that's how we do it. So result is interesting, and we have 3 methods here: traditional machine learning method, and we have the FCNN, which is fully connected neural network, and CNN and convolutionary neural network. You can see clearly, and it performed very well, and all the machine learning method in this case, and the deep learning, deep neural network perform better. And it's also worthwhile to mention 2 things. One is you can see we have the good pole looks good, the results are good, and the bad pole actually, and then result is not as good as good poles, and the new pole has less variation. Now it's more interesting come to the blind testing. Blind testing and the deep neural network obviously outperform the traditional one, and with result F2 missing assessment, and compare with traditional machine learning method of 1, 2, 3, 4, 5. So it is important to mention this. I'm running a bit out of time, so I will make it a bit quick. And we have set up criteria as likelihood damage, and which is a statistically percentage. And then so-called accuracy is less meaningful for industry. Okay, accuracy combined a false positive, which is a good pole has been considered as a bad one by prediction, and the false negative, which is more serious, and which is when damaged pole hasn't been detected and regarded as good poles. So false positive representing the cost, and false negative representing risk. So if you look at this graph, and when you're setting different damage and likelihood as criteria for bad poles, and then it gives you different result. The highest accuracy is when you set 40%, but that may not be the best for industry.
industry may want to have no false negative, no risk, and then they will have some of the cost, which is have false positive, and result in to 89% of the accuracy rather than the 93% accuracy. So with this graph and with our work, an industry can choose which one they want and for their assets management. All right, I run out of my time. This is the conclusion, and you probably already concluded yourself during my talk. And I would like to thank you for your attention. And if you have any question, and I'm very, very pleased to answer it.